Hello everyone. Today let's solve the problem Fenwick tree. Right. So this was asked on Codeforces round 2942 division 1. Right. So let's see what the question states. You can just go through the question. It's easier to understand. I'll just summarize the question so that it will be easier for us to solve the problem. Right. So just give me a second. 1 second. Yeah. So let's see what the question states here. We are given an array B. We are given an array B of length n. We have been given an array B of length n and an integer k and integer k. Right. So we need to find the array A. So we need to find? We need to find the array A. We need to find array A. Just remember this one. We need to find array A such that applying the Fenwick transformation k times, what we need to do? We have to apply k transformation, k Fenwick transformations, right? So I'll just go with k Fenwick transformations, right? So this is the main question, right? So again, I'm going to read out this one loud. We are given array B of length n and integer k. We have been given array B of length n and integer k. We need to find array A such that after applying the Fenwick transformation k times, after applying the Fenwick transformation k times, right? So the transformation uses low bit of I to define the sum range. So this is very important, man. So this is the formula basically, right? So this is the formula, nothing but low bit of I. You can just Google it, or I'll just explain this one later, right? So the transformation uses low bit of I to define the sum range. Or let me do it, let me do one thing, let me explain here itself, right? So basically, low, when I say low bit of I, it is nothing but S of I equals this one, A of I minus low bit LB I will write, low bit of I plus 1 plus 1, right? So same goes on, right? Plus same goes on until A of I, A of I. So this will be modulo mod value accordingly with the constraints, right? So this is basically low bit. So this is the formula we'll be making use of, right? So S of I equals A of I minus low bit of I plus 1 plus until this one plus A of I, totally this one will be going with a mod value, right? So we will reverse the process using mathematical convolution to recover A from B. So we will be reversing the process using the mathematical convolution to recover A from B. So they have strictly asked us to use the binary index tree and pre-computed factorials or inverses for efficiency. Binary index tree in the sense we have to make use of Fenwick tree, and they have also said that we have to go with the pre-computed factorials or inverses for the efficiency. Means we have to go with the binary index tree and the pre-computed factorials or inverses for efficiency, right? For the efficiency. So this is the question mainly. So this is the question, right? So uh, let me come here for the input output part, right? So let me explain you one thing. Just give me a second here. Yeah, we have been given two inputs here. Two indicates that we have been given two inputs, and this 8 and 1. 8 is nothing but n here. 8 is nothing but n, and k is nothing but 1. 1 is nothing but k. N is 8 and k is 1. N is 8, k is 1. So this 1 to 1 4 1 to 1 8, whatever they have given, this is nothing but the array B. In the question we have already discussed this one, right? So we have to output the array A. We have to output the array A accordingly with the criteria that they have mentioned in the question. So the same goes with the this one as well. Input 2 as well. 6 and 2 are n and k, and this one 1 4 3 17 5 16. This is nothing but the array B. This is nothing but the array B, right? So I hope the Fenwick tree part is completely clear, man. I hope the sorry, input output part and Fenwick tree part means here the array, this one, right? So basically we have to make use of the BIT here. Basically we have to make use of the BIT or the binary index tree or the Fenwick tree, and we have to go with the pre-computed factorials or the inverses for the efficiency, right? Pre-computed factorials or inverses for the efficiency, for the efficiency. So I hope this part is completely clear. So the output that we need to get here is, for the first input we need to get the output this one, and for the second input we need to get the output 1 2 3 4 5 6, this one, right? So I hope the question and the input output part is completely clear. Now as we are completely familiar with the question and the input output part, so move let's move on with the approach part. First we'll be discussing the approach, followed by the this one complexities, and then let's write the code as usual. First let's discuss the approach. So I have considered the same first example that they have given in the question here, right? So n we have been given 8, k we have been given 1. So initially 2, whatever they have given, it indicates 2 inputs, right? So that one I have not considered here. I have considered from n, k as well as the b accordingly with the question, right? So n we have been given 8, k we have been given 1, and b we have been given 1 2 1 4 1 218, right? 1 2 1 4 1 218. So this is fine. So the output that we need to get here is triple one triple one and double one, nothing but 8 times 1, right? So we will be going with a Fenwick tree. So we will be going with a Fenwick tree. Just keep this in mind. We'll be going with the Fenwick tree or the binary index tree, right? Binary index tree, BIT, also known as BIT. So let's move on with the further things. So let's move on with a step-by-step explanation, right? So as I've said earlier, we'll be going with a low bit of I formula, right? So low bit of I formula, we have considered this one during the question itself, right? So first we have to understand the Fenwick tree definition. So here, this is nothing but the low bit formula. S of I equals sum of A of j, where j belongs to I minus low bit of I plus 1 comma I, right? So where both this one low bit of I equals I and minus I, this part is Fenwick trees part, we know this one, right? So if you would have solved the Fenwick tree, you would have known this one, right? So this one low bit of I is nothing but I and minus I, nothing but lowest set bit of I, lowest set bit of the I and minus I. So this we need to know. So that is the reason I'm starting with the basic problem. The name itself suggests that. So basically the problem name I'm speaking of, the name itself suggests that it is a Fenwick tree. The question name itself is a Fenwick tree, right? So here S of 1 equals A of 1. S of 2 equals A of 2 plus A of 1. S of 3 is just A of 3. S of 4 is A of 4 plus A of 3 plus A of 2 plus A of 1, right? So A of 5, you can observe one thing here. For all the odd numbers, it is just this one odd. See here, A of 1, A of 1. S of 3 equals A of 3. S of 5 equals A of 5. S of 7 equals A of 7. But for the even numbers, we are considering the previous one as well, right? So here you can see S of 2 equals A of 2 plus A of 1. S of 4, all the things 3, 2 and 1, right? A of 4, 3, 2, 1. Same goes with S of 6. A of 6 plus, in case of only S of 6, we are considering A of 6 plus A of 5. We are not considering this one 4 3 2 1. We are going with the A of 5, right? So for the S of 7, it is just A of 7. For S of 8, it is A of 8 7 6 5 4 till here, this one, right? So basically, S equals f of a, that is nothing but b equals, I have given this number 1 2 1 4 1 2 1 8. B will get the value this one basically, right? So you can just see the calculation part, 1 2 1 4 1 2 1 8, right? So this one, this is nothing but the b. This is nothing but 1 2 1 4 1 2 1 8 is nothing but b. This is for f of a, right? So basically b array. So we have to reverse the formula. So accordingly with the a question, so we have to go with the reverse. We have to reverse or inverse, right? So they have asked us to reverse or inverse. So we have to reverse the formula. Let's do one thing. Let's compute a of I in order from 1 to 8. 1 to 8, right? So why we are doing this? Because n we have been given 8, k we have been given 1. So we have the values 1 2 1 4 1 2 1 8. So which we have already got 1 2 1 4 1 2 1 8. This is nothing but b. We have to get the array a from b. We have to get array a from b, right? So we need to calculate for a. We need to calculate for a, not b, right? So here b equals 1 2 1 4 1 2 1 8, right? So here we have to reverse the formula. Let's compute a of I in the order from 1 to 8 by reversing their we're reversing this prefix sum, right? So we have already got this one b, so we are seeing the b now, and we know this part as well. We know this part as well from the input and from this formula s of I equals sum of a of j, where j belongs to this one I minus low bit of I plus 1 comma I, right? So just give me a second here. This one, first we have to go with the I equals 1, right? Till I equals basically 8 numbers we have, right? 8 numbers we have in the input, 1 to 1, this one b array we are considering, right? Till I equals 8 we have to consider. You can just look into the calculation part, man. I'll just explain one by one. You can just we'll be going with the formula, same formula. This formula will be applying basically s of I equals a of 1, s of 2, same thing we will be doing for I equals, this is for I equals 1, this is for I equals 2, so this is for I equals 3. This part, just give me a second. So here, let's continue with I equals 3, right? So just give me a second, 1 second here. Yeah, so we'll go with 3, 4, 5, 6, 7, 8, the same thing, right? Here, this is just the formula, man. This is just the formula, right? So we have already got 1, 2, 4, this one, right? So where we got the B here, this one, 1, 2, 1, 4, 1, 2, 1, 8, 1, 2, 1, 4, 1, 2, 1, 8, right? So here we are going with the same formula as I've showed. This one, s of 1, s of 2 to s of 8, 1 to 8, right? So this one, this problem is completely dependent on this formula itself, low bit of I, as I've said in the question. So this is completely dependent on the formula, this one, right? So this one will be s of 1 will be a of 1, so a of 1 equals b of 1, nothing but the value will be 1. So I don't have to explain this one, I'll just show the calculation part to you. You can just go through the same, right? You can just go through the same. For this is for I equals 2, we'll be getting the value 1, 2 minus 1, totally we'll getting the value this one, what do we call, 1, right? Let's move on with the next one here. I equals 3, right? So low bit of 3, the same formula, s of 3 equals what we have the formula here, this one, and the third one, we have s of 3 equals a of 3, right? So this one will be going with the same thing, s of 3 equals a of 3, nothing but a of 3 equals b of 3, nothing but 1, the value that we get here is 1, right? So same thing goes with 4. For 4 we'll get the value 4. For this one, yeah, total value will be getting 1, sorry, for the 4 we'll be getting the value 1. So for 5 we'll be getting the value 1. For 6 we'll be getting the value 1 as well. For the 7 we'll be getting the value 1. And for the 8 we'll be getting the value 1. For the calculation part, you can just pause the video. You can just pause the video and you can just look into the calculation. So I have already shown the this one. What do you call formula? This one. Again, I'm showing this one. How we are going. How we are doing the calculation. Basically, we are going with a low bit of I formula, right? So this is nothing but I have showed this one, s of 1 equals a of 1, s of 2 equals a of 2 plus a of 1. Same goes with s of 3 to s of 8 as well. So this one, right? So this goes from this one to this one, right? So till I equals 1 to 8, all the iterations I have shown you. All the iterations I have shown you, right? So the value that we got, the value that we got here, this one, the value that we got here is 8 ones basically, double one double one double one double one, or 8 times 1, right? So for the this one, the output that we got here is 8 ones, which is equivalent to the output that they have shown for the first example, or the first input within the question, right? First input within the question, or within the example one basically, right? So that is within the question, right? So our approach works absolutely correct. Our approach works absolutely correct. As we are completely familiar with the approach, let's move on with the complexities part, right? So let's move on with the complexities part. So uh, what is the time complexity? Yeah, the time complexity would be big O of n log n. So the time complexity is big O of n into log n, right? So just give me a second, 1 second here. Why it is big O of n log n, not the logarithmic n per test case here? So this is per test case, right? So big O of n logarithmic n into logarithmic n per test case, because for each I we may traverse logarithmic n previous elements due to BIT structure, because for each I we may traverse log n previous elements due to bit structure. Again, I'm telling for each I, we may traverse logarithmic and previous elements due to bit structure, nothing but binary index tree structure, right? So overall time complexity would lead to big of n log n. So what would be the space complexity here? The space complexity would lead to big of n plus log k. Why it is n plus log k? So we will be making use of the, or we will be going with the array of size and this n part. So we will be going with the array of size n, this one array of size n, and also we'll be going with a fixed sized cache arrays. Also we'll be going with a fixed sized cache arrays. So I have written here log k. This is for this one fixed size, fixed size cache cache arrays, right? So this is it for the, this is it for the complexities part. Now we are completely familiar with the complexities and the approach, right? As we are completely familiar with the complexities and the approach, we are good to write the code. Let's start writing the code. So now let's start writing the code, right? So I'll just come to the compiler. We'll be making use of the different this one fast input and output. So I'll be going with the input output package, as well as we'll be making use of the uh, so I can just go with that's enough fast input output. So here let me go with import. So import java dot input output dot star. So this is fine. So let me go with a class name here. Class, I'll just give main. You can just give the question name or that is relevant to this problem. So I'll just go with the class main here. So initially what I'll do, we have to go with the max size of the array, as well as we'll be going with the modulo as given in the problem. They have mentioned the modulo value for the problem. So I'll be going with the modulo as given in the problem, right? So I'll just go with static final and max n. So let me go with this one. Why this is not taking, yeah, 4 4s and 5, the value basically, right? So this is the maximum size of the array we are considering, and also we have to go with the modulo as given in the problem, right? So let me go with static final keyword. So this one will be int mod equals double nine eight two, this one double four three five three five three. This is fine. So let me go with the further things. So now we have to store the modular inverses of numbers, right? So I'll just go with static long. So this one will be inverse new. This one is long. Let me pass the max, right? So next we have to store the modular inverse of factorials as well. So we'll be going with the factorial. So we have to store the modular inverse of factorials as well. So I'll just go with static. So this is long. I'll just go with the inverse factorial. This one will be new long. So let me pass maxen again. Right. So now we have to go with the cache for storing the power values. We have to go with the cache for storing the power values. Right. So I'll just go with static. So this one is long. Um, so this one will, I'll just name this one power cache or POW cache, right? So this one will be new long of this one 64, right? So this is fine. Next let me go with static long. So this one will be input array. This one will be new long, this one Maxon. This is fine. Let me come out of this one. Not come out of this one. Let's move on with the further things, right? So as I have said, we'll be going with the Fenwick tree. The question name itself says that Fenwick tree, right? So as we have already discussed in the approach, we will be going with the Fenwick tree or the binary index tree implementation, right? So let's go with the custom class Fenwick tree. So I'll just go with here static class. This one will be Fenwick. I'll just name this Fenwick tree, right? So within the custom class, so I'll just go with the size. Also let me go with long tree. So this is fine. Initialization part, let me go with the Fenwick tree. So parameters, I'll just pass in here. parameter. Let me assign size to n. Let me assign size to n, and also let me assign tree to new long of this one n plus 2, n plus 2. So this is one index, man. This is one index, right? So let's go with a void. Let's go with a update. So we will be going with the update query, range query, as well as the reset. These are the four methods that we'll be going within the custom Fenwick tree class, right? Update, because we have to add the values to all the responsible this one bit indices, or the binary index tree indices. We have to add value to all the responsible this one, right? Bit indices. So for that reason we'll be going with a update value. So I'll just go with void update. So this one is index, so this one will be value. So this is fine. Now we have to add value to all the responsible bit indices, right? So I'll just go with while uh, index less than or equal to size. This is fine. So let me go with tree index equals, so this one tree of index plus, let me go with value, this one mod. So this is fine. Index, so this one is index minus index. So this is fine. Let me come out of this one entirely. So next, let's go with the next method, nothing but the query. So I'll just go with the query. So this one in index. So within the index, but so what I'll do, let me initialize the sum to 0 first. So I'll just go with, this is fine. Let's go with the standard bit prefix sum. Let's go with the standard bit prefix sum. Let's go with the while loop. So this one index greater than 0, while index is greater than 0, I'll just assign this sum to this one will be sum plus tree of this one index. So this is fine, tree of index. So let me go with modulo mod. So this is fine. Next, again same thing. Let me assign index equals index minus, as this Fenwick tree. Again, let me go with the index ampersand minus index. So this one hyphen index. So this is fine. Next, let me return the sum. We have to return sum, nothing but here. So this one will be return sum, right? So let me come out of this one entirely. Let's go with the next method, nothing but the range query. So this one is long range query. So this one is int left comma int right. So this is fine. So within the range query method, we have to query the sum from left to right. Nothing but I'm speaking of inclusiveness here, right? So query sum from left to right. So I'll just return here. This one will be query of right minus query of left minus 1 plus mod. So this one modulo mod. So this is fine. Let me come out of this one entirely. Now next, let's go with the method reset. So I'll just go with void reset. So this is fine. We have to clear the tree for the next test case. So let's go with the iteration part now. So I'll just go with for int I equals 0, I less than or equal to size. So I'll just go with we have to go with the size plus one, not the size. So this one will be I plus plus. So this is fine. Tree of I. This one, let me assign this one to the 0. Let me come out of this one entirely. So now we have to go with the fast input reader. So this is just for the buffered, what do we call this one? Input output, right? So this is related to the input output, nothing but we are going with the fast input reader, right? Buffered input basically, right? So I'll just go with the custom input this for this for this particular problem. So I'm just gonna copy paste this one, man. I don't want to type the something. Basically, this is not the logical part. This is just related to the input output. So let me copy paste the input reader, nothing but the buffered reader part. So just give me a second here. So let me come here. Let me paste this one over here. Right. So next, let's continue with the same. This is just related to the pure input output part. So next, let's go with the scanner object. So I'll just go with static here. First scanner sc equals new fast scanner. So this one system.n. So this is fine. So the next step is we have to pre-compute the inverses and inverse factorials up to max n, right? So I'll be going with the pre-compute inverses method, right? So as we had discussed earlier, so we will be going with the factorial or the inverses, right? So we have to go with the we have to pre-compute inverses or factorial part, right? So we will be going with the pre-compute inverses and also inverse factorials up to max n, right? Also inverse factorial up to max n. Let's go with the pre-compute inverses method here. So now let me go with static void pre-compute. This one will be inverses, right? So this is fine. So within this method, what I'll do, let me do one thing. This will be inverse of 1. Let me set this one to 1 initially. Initialization. Let's go with the iteration part after the initialization. We are done with the initialization, right? So this will be as we have already went with the inverse of 1, we have initialized that one to 1. We have to go with the 2 now, right? So this will be int I equals 2, mm, I greater than max n, and let me increment this one I plus plus. So this is fine. So let me go with inverse of I. So this one, let me go with mod minus. So this one will be mod by I. So into, so this one will be inverse mod value we have considered already, right? So just give me a second. Mod value I have not initialized at all. Somewhere I have this one, right? So this is fine, man. So I forgot that one. So they have mentioned in the constraint the mod value basically, right? So this is fine. Inverse mod. This one has to be. We are going with a modulo mod. We have to go with, right? Mod minus mod by I. So inverse of this one mod modulo I, this one as modulo mod. So this is fine. This is fine. Let's move on with the inverse factorial now. So we are done with the inverse. Now we have to go with the inverse factorial initial array. So this one inverses of inverse, this is inverse factorial, right? So I'll just go with the inverse factorial of 0. Let me initialize this one to 1. So let me go with the for loop here. So this will be int I equals 1, I less than max n, so I plus plus. So this is fine. So this one will be inverse factorial of I. Let me assign this one to inverse factorial. So this one will be I minus 1 into inverse. So this one has to be inverse of I uh, modulo mod. So this is fine. So let me come out of this one entirely. So now we have to solve the each test case, right? So this is again related to the input output part and a bit of logical part as well, right? So now let's do one thing. Just give me a second here. We have to solve the each test case, right? Right. So let's do one thing. Let's go with the solve method, man. So I'll just go with static here, void. So let me go with the solve throws input output exception, input output exception. So within the static method, this one solve method. So let me first initially let me go with the length of the array, then let me go with the number of times that we have applied the f, so this will be first. Let me go with the length of the array. This will be sa dot next int, sa dot next int. This is fine. Next we have to go with the number of times f applied, right? So let me go with long k equals sc dot this one will be next. Instead of the next int we have considered long, so I have to go with the long here. So this is fine. Next we have to read the input, nothing but b of I. So this is one based indexing accordingly with the approach that we have discussed. So we are reading b of I now, reading the input b of I. This is one based indexing, we know this one, right? So let me go with the iteration part. We have to read each number, so we have to go with the iteration. So this will be I equals 1, I less than or equal to n, so this will be I plus plus. So this is fine. Now let me go with the input array. Where is input array? This one, input array of I. Let me assign this one to the sc dot next long this one, right? So this is fine. So let me come out of the for loop. So now, if you remember, I said we went with the cache powers, right? POW cache. So now we will be going with the cache powers that is used in the convolution coefficients, right? So now we will be making use of cache powers that is being used in convolution coefficient. So I'll just give here per power cache or POW cache, which I've considered this one of 0. Let me assign this one to the 1 initially, right? So let me carry on with the, let's move on with the this one iteration part. So this will be d equals 1, d less than 64, and let me increment the d plus plus. So this one will be power cache. So yeah, this one will be d. This one will go with power cache. So this one will be d minus 1. So into, so this will be k minus 1 plus d. This is fine. Mod. So this is fine. Modulo mod. So yeah, we are done with this part, right? So now let's go with a bit instance. So we have considered Fenwick tree, name Fenwick tree, right? So I'll just go with Fenwick tree. So this one, let me make use of the variable name Fenwick. We are going with a bit instance. So let's create it first. New Fenwick tree, new Fenwick tree, right? So we have to pass n here. We have to pass n. So this is fine. Now we have to go with the invert convolution to get the iterated value of the a. To get the iterated value of a. So this one will be for int I equals 1, I less than or equal to n, I plus plus. So this is fine. So within the for loop, so I'll just go with long subsum. This one, let me assign this one to 0. Next, let me go with int low equals I minus I, and this one is minus I plus 1, nothing but low bit range start, right? So now let's go with a simple for loop. So this will be for int j equals low and j less than I, and this will be j plus plus. So within the for loop, let's go with a hash of steps from j to 1, j to I, sorry, j to I. So this one will be bit def. This one will be integer dot. We haven't made use of the bit count, so I'll just go with a bit count here. So this one will be I minus j. We are going with the steps from j to I, right? So this is fine. Next, let me go with the coefficient. So nothing but coef here. So this one will be power cache. Nothing but we will be going with a bit difference within the array, and let me go with inverse factorial. Inverse factorial method, we have already written this one, right? Inverse factorial method. So I'll be making use of the inverse factorial. Let me pass again the bit difference within the array modulo. So this one will be mod. This one will be mod, right? So this is fine. Now let me go with the subsum. Let me assign this one to subsum plus input array. So this one will be input array of j, input array of j into this one will be coefficient modulo, this one will be mod, modulo mod, right? So this is fine. Somewhere I have missed, oh, I have messed it up here basically. This one I have to close the parenthesis here. So again I'll just go with the mod, right? So this is fine, man. The next step here, we have to recover the iterated value of the a, right? So I can just write here input array of I, this one input array of I minus subsum subsum. So this one again plus mod, also will be going with the mod value here. So why this is taking like this one? Oh, somewhere I, so this is fine. Mod though, so this one will be modulo mod, right? So this is fine. Modulo mod. Hope this is fine, man. We are just recovering the iterated value of the a. Next we have to update the bit, right? So we have to update the bit. For updating the bit, so I'll just go with Fenwick. So we have already written the update method. So here, this one I'm speaking of. Within the Fenwick tree, we have written the update method, right? So this one we are making use of. So we are not going with the update method for this particular problem. Somewhere we wrote update, right? So just give me a second here. So yeah, the first method itself was the update method, right? So I got confused here. Sorry, man. So this is fine. Fenwick dot update here. So this one, let me go with the I comma input array of I. So this will be input array of I. So this is fine. We are just updating the binary index tree here. So let me come out of this one entirely. Now we have to recover the output array A. So we have to calculate the output array A itself. Now we have to recover the output array A, right? So now we have to go with the individual numbers. So let me go with the iteration part. So this will be int I equals 1, I less than or equal to n, and let me increment I within the for loop. So we have to print this one iterated value of the input array, and also we have to leave the space accordingly with the output, right? So you can look into the output part, how we got the output, right? So this will be iterated value of the input. We have space between the numbers, right? So we have to display the iterated value of the input array along with the this one space between the numbers. So I'll just go with the space here. So this is fine. So the next part would be I'll just go with here println again. So we don't have to print anything, so I'll just leave it as it is. I'll leave it as it is, right? So let me go with the, we are done with this part. We are done with the solve method. Basically we are left with only the main method, right? So we have already written the solve method, so we just have to call the solve method within the main method, right? So we just have to call the solve function or the solve method within the main method. Also let's go with the pre-compute inverses method. Also we have to call the pre-compute inverses method as well within the main method, because we are pre-compute inverses is required for the division and division mod, right? So division small mod to the mod value that we have considered. For that reason we need pre-compute inverses as well. So somewhere we have written the pre-compute inverses man, just now I have written. So this one I'm speaking of, right? So let me copy this one before this one. So I'll just go with the main here. So here I have to give this one, I think throws input output exception. So I'll just go with input output exception. So let me delete this one. So we are this one. We require this one pre-compute inverses method for division mod. So I'll just go with the this one. Let me paste this one, sorry, not copy. So basically we are just calling the pre-compute inverses method within the main method, because it is required for the division small mod mod, the value that we have given big this one mod in caps, right? So that one. So now we have to go with the number of test cases. So this will be basically in the first example we had two test cases, right? So we have to go with the number of test cases. All other test cases we have to consider, right? So this one will be scanner. The variable we have considered sc. So I'll just go with sc dot next int here, right? So next int. So this is fine. So the next line we have to solve each test case. We have to solve each test case. So I'll just go with while t minus minus this one, if it is greater than 0, then what we will do, let me go with the solve, method, right? So we are solving the each test case here. So we are done with the coding part. Basically we are done with the coding part, right? So before checking the code with different inputs, let me copy paste the signature starter template. Just give me a second here. So let me come here, we paste it over here. Let's concentrate on the logical part now. So let's do one thing. We have to check the code with the different inputs, right? So let me copy this one. We have to get the output this one. 1 2 3 4 5 6. Let's check. So let me run this one. So just give me a second here. So now we have cannot find the symbol. Where? Class input output exception class man cannot find the symbol. 153. This one is 120. 120. This is fine. So this is solved through input output exception. This I have given correctly, right? So what's the problem here? So what happened here? So input output exception, this one, so I have misspelled here, man. This one will be input output exception. So this is fine. Again, the same thing I have done for this one as well. See here, I have misspelled E and P. So this one, where is it? Line number 153. So yeah, exception. This is fine. Let me run this one again. Now, yeah, we are left with one error, nothing but here cannot find the symbol. T for the test case, T we have already. So here, the last one, right? So we have considered T somewhere. I have considered this one. Int, this is not N, man, this is T. So we are going with the number of test cases, right? So while discussing, I said we will be going with the number of test cases as I heard the number as I have heard the this one, what do we call the string number. So I had given n, I think. So this has to be t. I have considered t the same thing, right? So yeah, this is fine. Now let me run this one. It has to give us the correct output. Let's see. Now we are getting the correct output. 123746. So just give me a second. 1 second. So what mistake I have done here is we are not getting this one in the single line, right? So instead of print, I have given println, I think. So where we are going with this one, where we are printing. So this one, this is fine, man. Just give me a second. I have to search for system out println. The code is long. So where we are printing within the solve, right? So just give me a second, 1 second. So somewhere we have made use of the, so pre-compute inverses. This is fine. This is not the case. Nah. System out println, yeah, we are doing this one within the solve actually, yeah. So here what, yeah, I have given println. This one has to be print actually. This one has to be print. So this is fine. This has to be println. We are not printing anything for the input array within the same line because we have to go to the next line. So for this one we have considered println because within the same example we had two inputs, if you remember, right? So we have to go to the next line and we have to print for the next input. But within this print, while printing the input array, we just have to leave the space and we have to print all the numbers in the same line. Now, yeah, we are getting the this one, but we are getting the output correctly. This one we are displaying the output correctly, but this one has to be all the ones, right? So we have already discussed the same thing within the approach. All the ones we have to get as output. So this one has to be 4 as well. 1 2 3 4 5 6, if I remember. Just give me a second. Yeah, this has to be all ones. 1 2 3 4 actually. Somewhere we have done wrong. So let's check this one. What we are calling this one within the main method, we are calling pre-compute inverses as well as solve, right? So first let's go with the pre-compute inverses. Here Let's check this one. Yeah, here what mistake I have done. So this has to be less than maxen, not greater than maxen. So let me run this one. Yeah, now we are getting the correct output. See, all the output. So this has to be less than the maxen, right? So this shouldn't be greater than maxen. So this is fine. Now we are getting the correct output, right? So let me copy this one entirely. So let me come to the submission part here. So I have already selected. This is the C, right? Question C, this one, Fenwick tree. So this is fine. Let me paste it over here. Let me paste the code over here. So this is fine. Let me hit the submit button. I hope this works for all the test cases, man. I hope this works for all the test cases. Let's wait for some time. Let's wait for some time. So here you can see running on test one. Let's wait for some time. I hope this works for the all the test cases. Let's see. Yep. Yeah, and the toast you can clearly see it is showing accepted, right? So the verdict accepted. So this is fine. Whatever the code that we have written works absolutely correct for all the test cases. We have considered the mod value basically that they have given in the constraints or the question. So this one is nothing but the array size. Array size we are considering. So manually we are considering the array size, right? So this is fine. And we are going with the Fenwick tree. Fenwick tree along with the this one. We are pre-computing the inverse. Along with the factorial inverse factorial as well, right? So this is for the Fenwick tree. You can understand this one. We are just going with a custom Fenwick tree class. So we have solved n number of problems using the segment tree and the Fenwick tree one by now, and also some of the problems on the sparse table. So I had written the blog on this one, sparse table as well. So I thought of writing the blog on this one, segment tree and the Fenwick tree as well, but I was solving at that point of time. I had already solved this one, many problems on segment tree, and I have given many contests basically, which basically consisted of the Fenwick and this one segment tree problems, right? So this is the third year I'm going with this one. What do we call uh, competitive coding, right? So this one, whether it may be Codeforces. Initially, I used to do with the this one in the by making use of the programming language Node.js. So now I'm doing completely with the Java. Now I'm completely doing with the Java. Basically, I thought of doing it in the C, but I had completely forgotten C, basically, to be frank, when I started. So I gave using Node.js. So now I'm just completely going with the Java, basically, right? So now, mm you can just check the blog on this one, sparse table. So after after completing these problems, I'll just write the blog on this one, segment tree, Fenwick tree, as well as this one, sparse table, right? So we are left with only three topics, right? So now we are solving the problems on this is one topic, solving the problems on a segment tree, Fenwick tree, and the sparse table, 15 problems. Next we'll be going with a complete advanced dynamic programming, right? So we'll see 1ddp as well as the 2ddp, right? So that is one thing, and the final topic will be graph. Basically we'll be going with a advanced graph. So we'll see different algorithms, right? Different algorithms implementation, right? So within the graphs, so within the dp, mainly 1ddp and the 2ddp. So here within the segment tree, we have to understand the custom segment tree, Fenwick tree, this one class, and we have to understand the sparse table. We have to understand the sparse table. So when update is not required, see here we have made use of the update, right? So when classic update is required, we'll be going with the Fenwick tree usually, right? So when the this updation is not required, usually we'll be going with the sparse table or the segment tree. So one thing I'll tell you, so whenever we are solving the problems on segment tree, bit, or the this one, Fenwick tree, or the sparse table, just remember this one. Every problem that could be solved by this one, Fenwick tree, we have solved this particular problem using the Fenwick tree. Every problem that could be solved by Fenwick tree can be solved by segment tree as well, right? So any problem that can be solved by Fenwick tree, that can be solved by segment tree as well, but uh, it is not vice versa. Any problem that we can solve with the segment tree cannot be solved by Fenwick tree. Some of the problems are solvable by Fenwick tree, whatever the problems that can be solved by segment tree, some of the problems can be solved by Fenwick tree as well, but it is nowhere written that all the problems can be solved using the Fenwick tree, right? So this is the difference. Any problem that we solve using the Fenwick tree can be solved by segment tree as well, right? So it's not vice versa. Any problem that we are solving using the segment tree cannot be solved by the this one Fenwick tree. Some problems we can solve, but some problems we cannot. Just keep this in mind. Also, whenever there is updation required, we will be going with a usually we'll be going with a Fenwick tree, right? So whenever the updation is not required, in that case we will be going with a sparse table. You can just read the blog of mine. I have written that one and I have shown the examples in the node. I have shown the example in the node. So same thing. You can just relate to the this one. You can just relate with the Java as well, right? So I have written the code in JavaScript basically in Node, as I've said. So I can just relate the same thing in the Java, man, right? So Java and JavaScript both are brothers. So almost same syntaxes, except Java is kind of heavy, right? Except Java is kind of heavy, right? So I hope this part is completely clear. This is nothing but the let's move on with the this one further things. So here this is nothing but the custom Fenwick tree class, right? So this is nothing but the custom Fenwick tree class, and this one fast scanner, whatever I have made use of this part. So this is nothing but what do you call fast scanner? What do we say this, man? How do we say this? How do I say this? This one is nothing but the input output part, right? So this one is nothing but input output part, um, fast input part. So custom fast input. So fast scanner we have made use of, right? So I just copy pasted this one as it was completely related to input output. You can just go through this one. This I have made this one as a template, so you can just go through that one if you want, right? So this is a main part along with the Fenwick tree, custom Fenwick tree part. So we are going with a pre-compute inverse. So two things we are going with. One is inverse and another one is inverse factorial here, right? So we are going with a pre-computing inverse, also inversing the factorial, right? Also we are going with the inverse factorial. The same thing we are these two things solve and this one. So Fenwick tree part we are making use of it within the solve method, and we are calling that solve method within the main method. And also the pre-compute inverses method that we have written, this one we are calling the same within the main method, right? So this is nothing but we have to read the test cases, right? So I mean we have to go with number of test cases, right? So but for that one we have made use of the variable t here. We have to print or read the individual test cases, which comes with individual test cases means within the same example we have been given two inputs here, right? So that we have already written within the this one fast input output method, this one I'm speaking of. So we have two inputs here. One is this one, we have already discussed this one in the approach. The second one, I insist you to try out the second this one input uh, in the same way that we discussed for the exam, this one input one. So you will get the question, I mean you will get the question clearly, man. You will get the question clearly, right? So I hope this part is completely clear. I hope this part is completely clear. So we are done with the problem, right? So I hope the solution part is completely clear along with the complexities and the approach. For now, this is it. Thanks for watching, guys.